This lesson deals with Supplemental Problem 16.4. You can find this problem in the ECE202 ebook in the Chapter 16 Supplemental Problem starting on page 6. The left side of the circuit below is the output stage of a transistor amplifier. At the upper end of the audio band, around 15.9 kilohertz, I have a load here that's fixed of 500 ohms. Could you find the load reactance and the turns ratio of this transformer such that we get maximum power delivered to R sub L? And then could you find the value of L needed and the power delivered to R sub L? Let's first find this impedance Z of S, which is the parallel combination of R sub S and C of S. So the impedance would be 1 over the conductance plus the susceptance. So 1 over R sub S plus J omega C sub S. So 1 over 400 plus J, and then 2 pi times 15.9 kilohertz is 100 kiloradians per second. So that's going to be 10 to the 5th, and then times the capacitance of 50 nanofarads. This turns out to be 2.5 milli, and this is J 5 milli. Find the magnitude and angle of this in polar form. A little bigger than 5, so 5.59 milli. And the angle is going to be in the first quadrant, a little bigger than 45, and it's going to be the tangent of the imaginary over the real. That's 63.4 degrees. The reciprocal of this is 178.8, and the angle then is a negative 63.4. Let's put this into rectangular form. So 178.8 times the cosine of theta gives me 80. And then times the sine of theta gives me minus 160. Let's do a source transformation. Convert this into a voltage source in series with this impedance. So I sub S times Z of S is going to be my voltage, and then I've got this 80 minus J 160. Now looking into the transformer, using our formulas from chapter 15, page 13, the impedance seen looking into this transformer is equal to the load impedance divided by N squared. That's going to be 500 divided by N squared, and then X sub L divided by N squared. As we showed in chapter 16 on page 20, we get maximum power transfer when the load is the complex conjugate of the source impedance. This was in chapter 16 on page 20. So the real part would have to equal the real part, which would be 80 is equal to 500 over N squared, so we can then solve for N. It's going to be 500 divided by 80, square root, and that's 2.5. Now the imaginary part, these two need to be equal to each other, but opposite sign. So I've got a capacitor here, and then I got an inductor, so I can do that. 160 would have to equal X of L over N squared. So I can now solve for X of L. That's going to be 160 times 2.5 squared, and that's 1,000. And then the value of L is taking this value and dividing by omega, which was 2 pi times 15.9 kilohertz, or 100 kiloradians per second. That's a 10 millihenry inductor. Power in the load is going to be the current squared in magnitude times R equivalent. This is the power going into the transformer, but the transformer is lossless, and so all the power is transferred, and then the load has a real imaginary part, and then the power just goes to the real part. The current in this previous circuit is going to be our voltage, which is I sub S times Z of S divided by the total impedance of Z sub S and Z equivalent. This had a magnitude of 50 milliamps, and this had a magnitude of 178.8, and then we had 80 minus J160, and then we had 80 plus J160. And that turned out to be 55.875 milliamps. So my power to the load then is the magnitude of that current squared times 80, and that's 250 milliwatts. I'll show you how this works. Let's take a look at not adding this inductor. The current in our previous calculation is going to be the same numerator, but now we've just got 80 minus J160 plus the 80 of the reflected impedance of the load. And so the magnitude of the denominator is going to be 80 plus 80, or 160 squared, and then a minus 160 squared, which is going to give me the square root of 2 times 160. That's going to be divided into our numerator of 55.875 milli. So the power to the load then is that square of that current times the value of the resistance looking back into my transformer, which looks like 80 ohms with my turns ratio. It's 125 milliwatts. So by just adding this inductor and basically resonating with the capacitance in our circuit, we're able to double our power to the load. This is called designing matching networks in RF circuits, and we'll take a look at more of this in ECE202. This is Supplemental Problem 16.4.